Hey everybody, so this particular research paper is called Geometric Manifold Rectification for Imbalanced Learning. And flat out, the best way that I can put this particular research paper is it is the first research paper that I've run into in a long time now that is directly dealing with research areas that I'm specifically dealing with at the moment and have been dealing with for a while now, that they have done something more than me in that area, just calling it exactly what it is. And this paper is super interesting to me. They have solved a problem, like the problem to me, the remaining problem is the honest way to put it. So in simplistic terms, essentially, the best way to frame it overall is when you train a model, LM model, AI model, etc., right? And you train it on multiple tasks, task A, task B. There's overlap between those tasks, right? Like if you, so you train it on task A and then you fine tune it on task B, you degrade performance on task A in order to get that performance on task B when you fine tune it. And this is all known, right? And this has been known for a long time. This degrades the models over time, etc. And then so how exactly do you fix that is the question, right? Like that's the $1 million question within that. I now know how to fix that. Like that's been the question I've been sitting on. Like how exactly do you perform the surgery needed in order to pull this apart? And this particular research paper gives me all of the answers within it. And then I went through and then I've run through 3 different experiments. So usually I like at the end of these, like I give you like, here's the Colab notebook, which would be this one in this instance, right? And then it ignores the fact that there's actually like 2 prior versions of this notebook. So within that, I'll give you access to all 3 of these ones because it's like the progression within this particular area is important, right? Because I essentially like even post this paper, it took their findings from their paper and then like next step within that, right? So they show me how to they give me the mechanism to measure this overlap properly, which is what I haven't been able to do, right? Like, how exactly do you detect it properly? And they lay it out perfectly as to why I haven't been able to properly detect it. And then so once I'm able to properly detect it, how exactly and what is the best way to do that surgery, right? And then I'll show you my experimentations because my first experiment with it was catastrophically bad. Like if it were a patient, like the patient like immediately died, right? Like is how that would go. But I was able to progress further, and I'm now able to like move the scalpel in a very skillful way in this area enough to actually improve what over the baseline overall, which means that like I've dug deep enough to figure out exactly the mechanics here that I needed to. So let's dive into that. And then so within this, I call this is basin interference rectification via geometric manifold cleaning. And then so the source paper, Geometric Manifold Rectification, proposed by Wang, Leah, and Jia in February 2026, addresses a fundamental challenge in imbalance classification. The paper's key insight is that class imbalance is not merely a ratio problem, it's a topological problem. When a majority class introduces into the minority class manifold, the resulting overlap obscures the true decision boundary. Traditional methods treat both classes symmetrically and use uniform neighbor voting, failing to capture local manifold structure, meaning that exactly what I've been talking about for a while now, right? These manifolds, these basins, when they form, they overlap over each other, and that's the problem, right? And then so how do you detect that overlap properly, and then how do you separate that overlap properly is the key mechanics within this. And then so their core mechanism. GMR operates through 2 integrated components. The first is geometric confidence estimation, which replaces uniform k-nearest neighbor voting with inverse distance weighted voting. Closer neighbors exert stronger influence on class assignment, implementing a smooth manifold-aware voting mechanism. The kernel function naturally captures local density variations and provides fine-grained reliability scores for each sample. This is important here, this next one. An adaptive metric selection switches from Euclidean distance to cosine similarity when dimensionality exceeds 100, addressing the concentration of distances in high-dimensional spaces. And I'm going to come back specifically to that. The second component is asymmetric cleaning. Rather than applying the same removal criteria to both classes, GMR enforces strict majority cleaning, removing any majority sample with same class confidence below A equals 0.3 or misclassified by its neighbors, while conservatively protecting minority samples, removing only those with majority class confidence above B equals 0.7, capped at a Y equals 10% maximum minority removal, and this asymmetry reflects the fundamental principle that in imbalanced domains, minority information is scarce and must be preserved. Coming back up to this here very specifically, this is important, right? So essentially they're doing a math transition. They're going from Euclidean distances to cosine similarity above dimensions of 100. and so that's a very simple and simplistic statement in and of itself, but there's a lot to unpack, like what they're doing within that. Knowing what they're doing within that, why they're doing that very specifically, etc., is all important within this, right? Like I think, like a lot of people, they don't understand how people converge on these things, on these things overall, right? And this is like this right here is like how people converge on these things, right? Because flat out, you start diving deep into these things, and then you realize above 100 dimensions, Euclidean distance and Euclidean geometry doesn't work for that distance, so you need a better distance function, and then cosine similarity is like the one distance function that you can use. So if you understand all of those elements, you get to this point, you deal with this problem, and you actually deal with it on a high level. There's like only like one or two actual answers, right? Because you know that you need to account for this. And then so when it comes into the discussion, do you know that you need to account for this? Yes or no? If you don't, then you're in la la land. But if you do, there's only one or two possibilities, right? And then so if you run into anyone else that's ever dealt with the same problem, it comes into that same thing. And to me, that's kind of how these things kind of work and shake out within that, right? But so then we dive into theoretical foundations. The paper provides 3 theoretical results motivating the design. Lemma 3.2 establishes that asymmetric cleaning, removing proportionally more majority samples, shifts the empirical posterior probability of the minority class upward in overlap regions. Theorem 3.3 proves that inverse distance weighting reduces estimator variance compared to uniform voting when label noise increases with distance, a common scenario in overlap regions. Corollary 3.4 justifies the metric switch by noting that Euclidean distance discrimination degrades in high dimensions while angular distance remains informative. The empirical results. GMR was evaluated on 27 benchmark datasets with 7 heterogeneous classifiers using AUPRC as the primary metric. It achieved the best overall average rank of 4.22. That's kind of boring as to what they're diving into there. But so to me, the bigger part here is the bridge, right? Like exactly what I want to dive into within all of this. So from data space to loss landscape. The original GMR framework operates on training data. It identifies intrusive majority samples that penetrate the minority manifold and removes them. Our research extends this framework to a fundamentally different domain, loss landscape topology, by recognizing that multitask basin interference is structurally isomorphic to class imbalance. And this gives you kind of just a good chart to look at there. In multitask learning with a shared backbone, 2 tasks compete for the same parameter space. When one task, the dominant task with more data or stronger signal, is optimized, its gradient updates can push shared parameters in directions that the other task's loss basin, degrade the other task's loss basin. This is precisely analogous to majority class samples intruding into a minority manifold territory. And then that pushing that directionality is the important aspect of this. I'll go through the experiments here, like from 1 through 3, and talk about them more as to like how I was able to narrow down on this specifically, right? But that's exactly like what is going on is that it's like, so you have one basin that gets created, right? And then that basin creation in and of itself can push in it's the direction, right? Is like and pushed in other, like in the same direction as, say, like gradient B, and then that's what leads to the problem of overlap within this, and that's why it's hard to eliminate. So why existing approaches fail. Current methods for handling gradient conflict and multi-learning, like PC-GRAD, CA-GRAD, or Nash MTL, all operate in gradient space, attempting to find compromised directions when task gradients conflict. But these methods treat the symptom rather than the cause. They resolve gradient conflicts at each training step without addressing the underlying geometric reality. The basins themselves occupy overlapping regions of parameter space. GMR offers a fundamentally different primitive, identifying and removing the topological intrusion before the optimizer encounters it. Experimental results. The setup. We constructed a synthetic multitask learning problem with controlled interference. A shared backbone neural network, so 3 shared layers, 64 hidden dimensions, serves 2 regression tasks. Task A is the dominant task, which receives 2,000 training samples, and Task B is the subordinate task, which receives 400 training samples, so a 5-to-1 imbalance ratio. Crucially, both tasks depend on a shared set of 10 input features, dimensions 0 through 9, creating an inherent parameter space overlap that forces the basins to compete. So we essentially like wanted to make sure that we're getting like competing data within this, right? And then so for our baseline experiment, baseline interference measurement, training each task independently establishes solo baselines, while joint training quantifies the interference. And so that you can see this, right? So this is exactly, I've been talking about these concepts for a few years now, right? Like, it's, I don't know, it's like, I'm just gonna like go on this little tangent on this because it's so funny to me, right? Like it's, it's related, like the Molt book creator and all of that. I see that, and so like the Molt book creator, like he just recently got picked up by OpenAI, and that's like all in the news, right, etc. Like it's just all everywhere, blah blah blah. But like that's off of a particular research paper that was put out by Microsoft a month ago, a month prior to that, and there's like probably like 300-400 people that are like more, like far more advanced than the Molt book creator guy when it comes to those things overall, and would know how to do that. But it's all like just hype, I don't know, like humans are weird, right? It's the best way that I can put that overall. Like I always come back to that. But so within this, so when we train each task individually, right? So we train task A and then we train task B. That is very different than combining task A and task B. When we like train on both task A and task B, we get degradation on both, right? Like it harms both the performance of task A and task B, again, because there's basin overlap, right? And then so task B suffers significantly more degradation from joint training than task A does. It's 364% versus 259%, but there's still massive degradation on both, right? Confirming that the asymmetric interference characteristic of imbalanced multitask learning. This mirrors the imbalanced classification setting where the minority class is disproportionately harmed. Then we do spectral analysis of the basin geometry, and this is like the most important aspect of this. So we sampled 300 mini-batch gradients from each task using the jointly trained model and performed eigen decomposition of the gradient covariance matrices. The spectral alignment score mean absolute cosine similarity between the top 5 eigenvectors of each task measured 0.076, confirming non-trivial directional overlap between the basins. The eigenvalue ratio task A to task B was 43.56, reflecting task A's dominance of the shared gradient landscape, obviously. So iterative development, 3 versions, are 3 tests that we ran through. The path from concept to working implementation required 3 iterations, each revealing a deeper understanding of how GMR's principles translate across domains. The failures were as informative as the successes. Version 1, subspace projection. This was our version 1 was a big failure, right? Like the patient just like found out like died. And so the approach was the typical approach, like everything that you would do 100% typically around this. We applied GMR directly to raw gradient samples, labeling task A gradients as the majority, so class 0, and task B gradients as minority, class 1. After GMR cleaning, we then computed the principal subspace of cleaned gradients for each task and projected all gradients onto their respective clean subspaces during training. So, exactly as you would do very classically within this, right? Task labeling, removing labels off of the labels, etc., right? Result was an abysmal failure. The eigenvalue ratio inverted from 35.28 to 0.26. Instead of rectifying the overlap, it flat out just collapsed the dominant basin entirely. Like the basin just went to fell apart, crumbled, right? Task A loss rose to 7.9, while task B degraded to 2.43, far worse than joint training. Diagnosis: projecting onto the clean subspace discarded all gradient information outside of that subspace. This removed not only intrusive components, but also legitimate task A optimization directions. The analogy: treating a tumor by removing the entire organ. We just removed the entire structure, and it just all of the pillars, the supporting pillars, and they just fell apart, right? And then so okay, let's not remove all of the pillars. Let's go in and we'll just surgically cut out, right? And then that failed differently. And then so instead of projecting onto clean subspaces, identified intrusive gradient samples using GMR's geometric confidence. Then we extracted the principal directions of only those intrusive samples via PCA and built a projection matrix that removed only those directions from task A's gradients. Task B gradients passed through untouched. So we used specifically all PCA, right? So dimensionality reduction, etc. all around that. This is if you go past step 1, 90% of people would go to step 2, and then this again failed. So result: GMR found 0 intrusive samples across all configurations, even after escalating the strictness threshold from 0.3 to 0.7. No task A gradient samples were classified as belonging to task B's manifold. Diagnosis: the gradient magnitude distributions revealed the problem. Task A gradients had a mean magnitude of 1.4, while task B gradients averaged 0.48 or a 3-to-1 ratio. This magnitude separation makes the gradient clouds trivially separable by KNN, regardless of their directional structure. GMR correctly determined that there was no spatial intrusion, but the interference is directional, not spatial. The gradient vectors share conflicting directions even though they occupy different regions of magnitude space. Version 3, spectral intrusion extraction, the working example. Our approach: we bypassed sample level analysis entirely. We used the eigenvector alignment matrix already computed during spectral analysis to directly identify task A eigenvectors that share significant direction with task B eigenvectors. These shared directions are the intrusion subspace, where task A optimization interferes with task B's basin. Built a projection out matrix, P equals, using a bunch of math, and then task B remained completely unchanged. So here's the bottom lines of the results of this, and then there's a lot to dissect within this overall. But so eventually, utilizing a spectral score of 0.05, we were able to improve the performance of the digger, pop out the dents of B, keep B's basin solid and improve B's basin while not degrading A's basin, which was the whole entire goal, right? Keeping these basins they kind of spiral around each other, and I'll show you. There's a lot of I have a lot of good visuals with regards towards what this looks like. I'll show you in a second here. But so this is the critical finding within this, the most important element of this that I need to get across, or else you won't understand what's going on within this until like this, right? And then so essentially the threshold sweep revealed the most scientifically significant result of the entire investigation. The relationship between the number of intrusion directions removed and task B performance is profoundly non-monotonic. This is not a smooth curve. Removing 3 directions, threshold 0.15, produces minimal improvement. Adding a 4th direction, threshold 0.10, makes things slightly worse. Adding 2 more, threshold 0.08, makes performance substantially worse, at plus 72% degradation versus joint training. But then, removing 15 directions, threshold 0.05, produces the best result by far, a 45% improvement. This points towards a phase transition-like structure in the intrusion subspace. There appears to be a critical threshold where enough of the interfering manifold has been removed that the optimizer can find a qualitatively different solution, one where the basins actually layer cleanly. Below that threshold, partial removal creates a worse geometry than no removal at all. The symmetry that the optimizer was exploiting is broken without providing a clean alternative. The specific eigenvectors matter enormously. Eigenvectors 11 and 18, added at threshold 0.08, have low eigenvalues, but their removal destabilizes training. Meanwhile, the lower eigenvalue directions added between threshold 0.08 and 0.05 provide the critical mass needed for the phase transition. Each failure provided a precise diagnosis that directed the next iteration. The V1 failure showed that subspace restriction is too aggressive. The V2 failure revealed that basin interference is fundamentally directional rather than spatial. Gradient clouds from different tasks don't spatially overlap, different magnitudes, but they share directions that conflict. This insight was only possible because the diagnostic infrastructure, spectral analysis, gradient sampling, and interference measurement was built into the experimental framework from the start. And then so diving very specifically into these experiments and then what we're going to look at visually here overall. So first of all, here's experiment number 1, right? Which was like we can now identify the intrusion boundary, and then now can we rectify it? And then the result of experiment number 1 was no. But so I'll go through. I'll leave a link to this so you can go through everything within this, right? So we create the 2 gradients, task A and task B, and then we essentially we look at them, and then we look at the combined gradients, right? So here's basin A, and then here's the basin for here's the basin for task A, here's the basin for task B, and then what happens is that you get this essentially this combined basin, right? And then we're able to before like this research paper before this, I wasn't able to get these types of metrics. So like this is like to me like amazing sauce, right? Like, and then I can see and I can plot out here's the task A gradients versus that like task B gradients, and I can see like, there's obviously overlap there, right? And they're obviously overlapping. So then I want to fix that, and then so we do this, and then I tried just doing like based off of like the research paper and gradient space exactly as outlined for this first experiment here, and like nothing happened basically. Like, and this is like you can see here, so it's like it didn't remove anything, like and then. But it does detect overlap, right? Like so that like overlap significantly detected. We're just not able to like remove stuff, right? And then like the major problem within that is like this gradient classification, right? We're not able to properly classify these gradients, and then so I go through. And try to essentially like fix it using utilizing PC grad, and then like these are very bad. Like it just like an explosion happened in the latent space. Is like a kind of like what happened, right? It kind of like set off like a bomb inside of the patient, I guess would be like the way to frame that overall. And you can see it you don't want spike, like generally like spikes, like huge spikes like this on the loss function. Like I don't know what's going on there. Like you generally don't see that. And you definitely don't want to see this like this flat loss function. You want to see it going down like this is. So yeah, this is all bad as to like what we're looking at there, but it's good stuff. Like sometimes you don't know where to go and which direction to go until you fail, and then you can fail. Okay, why did you fail, right? And you go from there. So that's what we're doing within this first experiment here, and we can see like this is the major like we just blew up the eigenvalue ratio, right? Like we just like set off a bomb in there basically, like and you can see that, right? Like minus 99.3%. Like we just blew up like all the structure, like all the structure is gone. Okay, cool, and then. We can see, yeah, that's exactly what happened. like so essentially, like this is the structure before, and then like this is like you can see our blast radius, right? We just put the bomb in there, and then so okay, that is what it is overall. And then so this is experiment 1. From that, what I learned was that this typical approach isn't the direction at all. Right? That we need to do something different within that, and then so. Within that, I set this up, and I go through, and then you'll go through here, task do, and sets this up properly, and then so we get our loss here, we get this here, and then we're gonna get an error right here, and then so if you look at this and you're like, okay, this notebook 2 isn't working, right? Notebook 2 is working perfectly. The reason why we're getting the error is because too few intrusive samples we detected, right? So we went through, same problem as within this one, where we went through that one experiment. We still aren't able to detect what's going on properly with these gradients. And then, so in this instance, I was using PCA detection. And then, so, okay, I wasn't able to detect exactly what's going on within this utilizing PCA or dimensionality reduction. So I need to switch to an approach. And then so I switched to like spectrograph. So like think more like resonance waves and things like that, right? And then that's where I'm able to like detect signal from these basins and then able to perform this improvement function overall. And then so that's kind of what we look at here with like experiment 3, and then experiment 3 is like where we get to kind of the magic, right? And then so lots of cool visuals in this one here. So this is like same as before, right? So this is the task A, and then the overlap for task B, and then what we can see is that this overlap is actually directional. So that's like we're able to get this measurement that we weren't able to before, and then also like this is like you can see the overlap here, right? So here's task A, and then like task A in blue, task B in red, and then like there's definitive overlap there, right? And then so we want to essentially like just cut here, right? This is our like where we want to like focus on within kind of our surgery attempts is what we're trying to do. And then we go through, and then so we like our method, like we tried essentially 2 different methods within this in order to classify these gradients, right? And then so our first method, following more traditional lines, again, nothing, zero detection, right? Okay, so like we failed on that detection again, and then we go through method B, which is that spectrograph. Okay, we get signal, we get intrusion detection, where we're able to pick up the signal within there, and we're able to isolate it, and then that gets us to meet like this is like the beautiful chart within this, right? So then this is like the like same charts, the same measurements, but like you need to measure this like in a very specific way in order to detect it, right? And then so like this is the basin for task A, and then what we can see is that very specifically the basin for task A has intrusion directions, like it's going in directions that it wouldn't be going in if not for task B. We've identified exactly what is going on within these problems, what's occurring within that, and what this problem is overall, right? For the very first time. And then so we can go through then, and then like can we like perform surgery, right? And then so that's what we go through. The answer is yes. Like we're able to perform surgery on this, like, and get some like okay results out of it, right? Like, but like we're able to cut, like, and it works within that. And like again, like the interesting like loss spikes within this, but like this is the most important one to me here, right? This is like you can definitively see the overlap when you chart and graph it out this way, right? Like, so like look at these, and these are the basins, right? Like, and so like basin A, basin B, and then you can significantly see kind of like how exactly that looks and works out there, and then like kind of how like this is like the whole rectification process overall, and then same thing here, right? Like it's exactly what we're doing. So we're essentially like our scalpel is going in, and then we have like this, and then we need to essentially like remove as much of this as possible, but we want to keep the structure, but we don't want to like remove the entire organ, right? We don't want to remove this, but we want to like lessen it. So here we go, like that to that, right? That's exactly what we did. Like we performed the surgery that we wanted to within the latent space overall, right? And then within that and post our surgery, we can see we've got it worked. We're able to essentially like stabilize, control, like decrease loss post surgery overall, and then in the like 15 eigenvector direction test, we were able to actually improve this overall. Like this was an improvement for the model overall, and then within those basins and that separability of those basins overall. And then so to me, this is like, I mean, again, like the last step within I don't know, like all of this, right? As far as like being able to get models to where people want them to be, like where in the world now where this exists, right? Here it is, like you're looking at it, right? Like to me, like last 3 years plus, and I think it's going to be for the next like decade, is like such an information disparity in the world that exists, right? Like even within my companies, right? It's just such information disparity as to like people that understand and know exactly what is capable at the moment versus what's not, is what drives all. I don't know. There's like like I've never seen such a big gulf of that in my life. Like, interesting to watch all of that play out overall. But so I'll have a link to these notebooks here as well as this research paper here. This solves a super interesting problem to me that I've been facing for the last 2 years. So I can't thank these guys enough. Like they to me, they put me over any hurdle that I needed in order to get to like what I'll call like the final layer, right? So here we are. And yeah, if you like this type of content, please like and subscribe. Thank you very much.